Um, the topic of this talk is quite a departure from the analysis we've been seeing, so please bear with me. But there's some geometry that produces differential invariance that has a very nice application in financial market data, right, among other things. Not going anywhere. Double. That's the battery. Yeah. So extreme value theory is at first sight maybe a very strange part of statistics. I remember the first time I heard that there was such a thing. It seemed outlandish that you could predict sort of beyond anything you'd ever seen before. And then this was around the time that Paul Embrechts published a quite famous book on the subject. And then when I looked at the book, I thought, well, if I was an actuary, maybe I'd want to read that book. So I just forgot about it after that for several years. But the questions are natural ones. So you have rivers that flood every once in a while. What's the 100-year flood? How do you prepare for that if you don't have any idea what flood might be worse than the ones you've already seen? You have to try to make some estimates of that. Something we've seen a lot of recently in the UK and other places, claiming temperatures are record highs. When you look at it and it's 0.1 degree higher than the previous high. And if you look at the tails, you see that actually wasn't anything unusual. So in a financial context, suppose you're in the short VIX trade, which has become popular again. What sort of 3-day loss level should you expect one time in 100? Right? And on average, if you blow through that level, what should you be ready for? How likely is a 1-week loss of more than 20% in WTI crude oil price? So the fact that there's a process in principle, for answering those questions, and in practice, from what we've now established, is a result of these quite remarkable limit theorems of extreme value theory. This is the 3 types theorems. There's 3 of everything in extreme value theory. You'll see if you already know this. But we've shown recently that there's a very good geometric reason for everything that goes on in extreme value theory. It's not simply some lovely analysis, which it's worked out with a great deal of difficulty over many years. There's a geometric explanation of all of this stuff. So we have new differential invariants that not only give a very simple characterization, makes it very easy for you to check whether your favorite distribution is in any of the limit domains of attraction, and if so, which one. Okay. But that's only part of what the invariants are good for, because they also give us an intrinsic way of measuring how far things are from their limits. How close to converged is this distribution at a given quantile? And that's a very nice bit of application of differential geometry to probability theory, but it's also led us to some very efficient tail models. So here's the starting point. You take an IID sample, n draws from the same distribution f. Then let x max be the sample maximum. Well, that's another random variable. Okay. What's its distribution? Well, if they're all less than if x max is less than r, all of the other ones have to be less than r2. So the distribution of the max is simply the nth power of the distribution f. So Fisher and Tippett, this famous statistician Fisher, addressed this question. It's actually, I thought it's fascinating. They published the answer to this question, which we now realize certainly has applications to financial markets. They published it a year before the crash in 29. Of course, nobody was imagining it had any application there. So they asked, so of course, if you just think about f to the n, stick it into your favorite computer, right? And what you're going to see something very quickly looks like a step function. Of course, it's not. It's really got some curvature in it. But to see that, you want to stretch it out. And you also might want to translate it. So they asked, can you find a sequence of, of constants an and bn, an positive, so that translating and rescaling, you end up with a limit distribution as n tends to infinity. Okay. Now, if you're going to have such limiting distributions, then they must be the limits of their own extremes. Right? There's no place for them to go. These things might not exist, but if they do, they're going to have this stability property that they're the distributions of their own extremes. And what Fisher and Tippett did, motivated apparently by some, Tippett worked at the Wool Institute in England, and the motivation was breaking strengths of wool fibers, apparently. So they, in a really awful, painful to read paper, they showed that there are attractors with this stability property. There are precisely 3 of them, or 3 types of them. 2 of them come with a parameter. Oops, sorry. The Weibull and Fréchet distributions, and the third is a point, Gumbel distribution. The Weibull distribution, of course, wasn't due to Weibull, but due to Fréchet. I think that the Gumbel distribution was due to Fisher and Tippett, but these are the names that they now have. So 8 years later, Richard von Mises, the brother of the economist, realized that it was really just one big one-parameter family. But to write it that way, you need to make variable domains. And the Weibull type is defined on a negative half-line, the Fréchet on a positive half-line. And then as the alpha goes to infinity, both of these things, in absolute value, both of these things end up with the Gumbel distribution as their limit, which is easy to check when you see the parameterization. Okay. So the punchline of Fisher and Tippett's paper was, oh, we can show that the limiting distribution for extremes of the normal distribution is the Gumbel distribution. But the convergence is slower than a tortoise in the middle of the summer. Just painfully, painfully slow. Anyway, what this was, though, was really a result about the existence of these attractors. They didn't have any general method to check. If I walk in the room with a new distribution and say, how about this one? They say, well, I don't know. We'll have to try a bunch of things. And so it was actually only 15 years later that this gap got filled in. And it got filled in by the Russian or Ukrainian statistician, Yudenko. In 1943, remarkably, in the middle of the war, this guy working in Russia managed to publish a paper in an American Mathematical Society journal. I don't know how. So he had a completely independent approach to the problem. I don't think it's even clear that he'd ever seen the work of Fisher and Tippett. But he gave a method, at least if I have a form, if I have the function in my hand, he gave a method for checking whether it was in either the Weibull or the Fréchet domain of attraction, really by looking at scaling properties, asymptotic scaling properties of the tail. Okay, and that's the one for Fréchet. So it's easy to check that. It helps to have maple maybe or something else to do some of the limits, but it's easy to check that. But it's also not at all clear why that has something to do with the nth power of the distribution. You see, the power's disappeared. No indication of the power there anymore. And the other thing that he did was to try to nail down in addition to the Weibull and Fréchet's, the Gumbel distribution. And he just, it really, there's a huge transition in the readability of the paper when he moves to the Gumbel. Quite clearly, he was never happy with his characterizations. And it turns out, in fact, he said explicitly, these aren't definitive, they're not practical, but they're correct, they're conditions. But it turns out that the key to Fréchet and Weibull is actually scaling invariance. But in the Gumbel case, it's translation invariance. And you can't get there through scaling. So I'm give you a rapid survey through this extreme value world. I apologize if you've never seen any of this before. But there's a second, I mean, again, decades go by. And then there's a second approach that makes a big, big difference in this subject. And that was independently by Picklins in the US and Balkman de Haan in the Netherlands, showed that there's a strong connection between what they called peak over threshold limits and these domains of attraction. So the peak over threshold idea is to look at the distribution conditional on being in excess of a certain threshold. And then ask, is there a limit, again up to location scale transformations, as that threshold tends to infinity if that's available, or to the upper end of the support of the distribution. Okay. So they proved this theorem, which is where we got generalized Pareto distributions. They said, look, there's this great family. In fact, it's 3 families again. The parameters exactly line up with the parameters that you saw in the extreme value distribution list. And these guys all have the corresponding extreme value limit as their attractor. Sorry? Oh, sorry. The domain of the distribution is alpha of f, omega of f. Okay? It's the right-hand endpoint, which might be infinity. Okay, sorry. Okay. And again, there's a point that's the limit of both ends of this one parameter family. But now, I mean, this is presented typically in the extreme value theory descriptions as if there's nothing to ask questions about. But it certainly occurred to me to wonder, what's so special about these distributions? I mean, everything that's in the domain of attraction of one of the extreme value distributions is getting close to everything else. Right? They're all going to the same place. What's so special about these ones? And it turns out that the geometry answers these questions. What's the connection between these extreme value limits and peak over threshold limits? Okay. So here's the geometry in a nutshell. The statisticians call this, the affine group on the line, the location scale transformations. Right? Those 2 parameters are responsible for the 2 parameters you see in all the textbook probability distributions, right? The change of scale and location. So what we're looking at is the geometry in the sense of Felix Klein. We want to know all the information that's invariant under that transformation group. Okay. Now this is a very natural group for probability. It's actually, Cartan and probably Lee proved that after the general group, the diffeomorphism group on the line, which doesn't preserve anything, right? Every distribution is the same as a uniform distribution, for example, if you use that. The next group down is fractional linear transformations, and they don't preserve the idea of a finite mean. And this is the next group, the next group on the list. There's nothing in between those 2. So Cartan produced an incredibly powerful set of tools for extending the initial results of Sophus Lee on differential invariants, symmetries, Lie transformation groups, finite and infinite, and so on. And Cartan's method of equivalence allows us to, it gives you a method of constructing a complete set of invariants. Right? It's a list of instructions. Sometimes they're very hard, or they may be impossible to carry out in practice. But you have this almost algorithm for cranking out invariants given, given Cartan's method. And the great thing about this approach to geometry is that it picks up the exceptional cases. So if you apply this in the case of surfaces, you'll find the exceptional cases are the constant curvature surfaces, and there's 3 of those. It turns out 3 types of those. Right? It turns out of course, if you make the group bigger, then the conformal transformation, so there's one class. So I'm going to give you the answer. It's almost like using a Formula One car to drive down the street to the corner store. It's an actual meaningful example of very simple case that you don't usually see in the equivalence problem, beginner versions. So here are the invariants. And we start with a distribution f. We're going to let I be its logarithm. That's well suited to looking at powers. And j is this combination of second derivatives, which you can immediately see is translation and scale invariant. The punchline in the Cartan method is that at some point you've got all the invariants that you're going to get. Everything else is dependent on the ones you've already got. They're derivatives. And the functional dependence is the encoding, the final encoding of the differential geometric information. So here we've got 2 invariants, but we've only got 1 dimension's worth of x. Right? So these things must be functionally dependent, and that dependence relation encodes the equivalence classes. So we'll come back to that one in a minute. But the stability property is given in terms of samples of size n, as n goes to infinity. So n's an integer. But it turns out that it's got nothing to do with integer powers of n. And the geometrically natural thing is to ask, well, what distributions f are in the same equivalence class as powers of f, where the equivalences are affine transformations? And the answer is the extreme value distributions. That's exactly what's characterized by that. And so the other thing it's easy to check is that the product of these 2 invariants I and j doesn't depend on the power. So that's actually the reason why the answers to what are the attractors don't depend on the power n, even though that's where the question started. And the exceptional distributions, the ones for which this curvature-like invariant is constant, are precisely the extreme value distributions. And there's only 3 types. Okay, they're positive, 0, and negative. So it's exactly analogous to constant curvature surfaces. And that's the parameterization, if you like. And if you want k to be a curvature, you should subtract 1 from it, so you get. So here's the first use of those invariants, and the fact that the constants pick out the extreme value distributions. You bring your distribution through the door and ask, does it belong to one of these attractors? And the answer is, well, compute the invariant and let x go to the upper endpoint, finite or infinite. Either you end up with the constant corresponding to one of the EVT distributions, or you don't. If you do, that's the domain of attraction it's in. If you don't, it has no limit. Okay? And von Mises gave a nice example of a again back in the 30s of a perfectly smooth distribution that has no EVT limit. And in our terms, what you see is if you start looking at the invariant, it very quickly falls into a periodic trace. So it just doesn't stay anywhere. So it's very easy to use that result to test, just pick up your favorite probability distribution list and test them. It's very simple. And of course, you can also verify from this that the generalized Paretos match up as we know that Picklin's et al. Said they should. Okay. But again, we still have this question of what's special about the generalized Pareto distributions, because so far they're just distributions with the same parameterization, the same, nice that the parameters line up, but you can check that the student distributions with parameter nu correspond to the fresh A with parameter nu domain of attraction. It's not impossible to get things lining up like that. It doesn't tell us why they're so important. So to see that, we're going to look at something basically dual to the peak over thresholds, which Anna likes to call peaks under threshold. But the same question, if you're going out to the to the other tail, look at the distribution conditional on being below a certain level, and ask if that has a limit as that level goes off to minus infinity or the bottom of the support. Well, again, the geometry tells you when that happens. That's precisely when this invariant J, which is Ixx over Ix squared, is equal to a constant. There are three types again. All the constants are available. And this is what they look like. So if those may look sort of familiar if you're familiar with the generalized Pareto distributions, and there's a good reason for that. So if you have a probability density function, then the mirror image density is obvious. Yeah. The mirror image density is obvious. And the distributions we've discovered are actually the mirror images of the generalized Pareto distributions. Okay. And so that's the theorem. There's a duality between these domains of attraction. So the exceptional distributions on one side and the duals of the exceptional distributions on the other side, those are the three types, EVT and generalized Pareto, and that's it. Nature only makes so many constant curvature examples. So now I'm gonna have to really speed up here. So the great thing about an invariant is for a probability distribution is you can evaluate it at quantiles. And now you've got something you compare two probability distributions. Quantile by quantile, you've got this way of measuring now how quickly something's converging. So we're going to put the slides on. So there's a discussion of that question, and I'll skip through it so I can show you some of the applications. So the efficiency of the generalized Pareto distribution is because it converges so quickly. Right? You don't need nearly as much data. Something's converging rapidly. You can get away with less data and still get decent estimates. Nevertheless, you'll probably have noticed that there hasn't been any incredible amount of extreme value theory successfully doing risk management in finance. The reason is that typically, to use the generalized Pareto distribution in these ways, you need thousands of data points, maybe 5,000 data points. Okay, so by the time 5,000 days have passed, things have moved out from under you. You have no ability to keep up with present conditions if you need that much data. So what we've been able to do in a way that still has to be kept under wraps is to really speed that process up. We can do it with very, very short data sets. I mean, a year of data, daily data is lots for us. Often far less than that. And these things, for example, so this is what we call risk timing. We're measuring the 100-day value at risk and the expected shortfall, the average loss beyond that. We're targeting a level. Say every time the level gets, the ES gets bigger than that, we're going to reduce our position. When it gets smaller than that, we'll put our position up a bit. And that's what we've done here for 30 years. So the beginning, the two curves are tight together. That's partly because of the tremendous, I should have put it on a log scale, but it's on a regular scale. But it's also because it's effectively been calibrating by matching the level of ES in the market for the first 10 years or so, right? And then just put it on autopilot for the rest. Right? And you see it just, one, it decided to have more risk than the market for a while in the run-up to the tech bust. It reduces the drawdowns tremendously. Right? So it's not because it knows in advance that something's going to happen, but it observes that the risk is getting higher. And so you're pulling the position back. So one recent example was the short VIX trade, which JP Morgan quant had a series of articles warning people by mid-2017 that if the VIX hit 20, people were going to be wiped out, totally wiped out. Of course, you know, if it gets to 20, that's bad, catastrophically bad, as it turns out, for lots of people. But how likely is that? Well, the VIX tourists, as they were called at the time, didn't pay much attention. They weren't worried. But in fact, we saw that this was extremely likely. I mean, likely enough to be very worrying. And in June, we said, well, look, it's once in 280 days. You've been doing this, picking up your pennies in front of the steamroller for months and months, years now. You've got a 1 in 280 day chance of going completely bust. Russian roulette with one bullet and 280 chambers, what we called it. But by August, there was a bump up in the VIX to 16, and that gave us a revised estimate saying there's only 48 chambers left. And so, you know, it should have been over within 3 months. It lasted 5 months, but of course, in February 2018, the surge came, the ETFs were wiped out, the lawsuits are still continuing. And as of last week, the VAR and ES that we're measuring for these things are significantly higher than they were in January 2018, and yet there's a recent record high in short VIX positions again. Oh, by the way, this is a slide that George asked Anna for yesterday. This is the VIX, the PDF corresponding to that distribution shifted to 0, 1, minus 1, 1. And the S&P back in 2008. So another quick example. Back in 2015, here's the Bloomberg article on the web. Jamie Dimon made a laughingstock of himself by saying a once in 3 billion year jump in bonds had just happened. That was a 40 basis point jump in the US Treasury in one day. Of course, his 30 billion years was based on a normal assumption, which doesn't make any sense at all. He was lampooned mercilessly. We looked at the high lows, daily high lows, and you know, 40 basis points wasn't anything extreme, unheard of. Every 2 or 3 years you should see a move like that. The point that was totally swamped by Dimon's blunder was the fact this happened in only 15 minutes. It was a flash crash, right? There was just no liquidity. So we told Jamie about this, but he hasn't gotten back to us yet. So, anyway, there are many more examples, and we'll put the slides on our website so you can see them if you're interested.
Okay. Thank you so much, Bill. Sorry that I had to rush you, but we are working on a short